Chapter 12. Principles for Secure Encryption. This chapter covers 5 principles for secure encryption, large blocks and long keys, confusion or nonlinearity, diffusion and saturation. Let's pull together everything we learned in Chapter 11. In sections 12.1 to 12.5, we will distill the 5 underlying principles that make a block cipher secure. One hallmark of a secure block cipher is that changing any bit in the key or any bit in the plaintext will cause about 50% of the bits in the ciphertext block to change, preferably in a random-looking pattern. Changing any other bit also will cause about 50% of the bits in the ciphertext block to change, but in a different pattern. Let's call this the 50-50 property. This chapter will describe how to make that happen. Section 12.1. Large blocks. We have seen that a bigram cipher can be solved just like a simple substitution cipher by compiling bigram frequencies and contact frequencies. This can also be done for trigrams and tetragrams, although a very large amount of ciphertext is needed. For block ciphers done by hand, the smallest block size that should be considered is 5 characters. For computer ciphers, the minimum block size is 8 bytes. One purpose of a large block size is to prevent Emily from solving the cipher like a code. That is, Emily would find repeated ciphertext blocks and deduce their meaning from their frequency and their positions in the message. To take an extreme case, if the block size is 1 character, then no matter how large the key is and how many encryption steps are used, the cipher is still just a simple substitution. There are numerous 8-character sequences in English that are common enough to appear repeatedly in a long message. Here are a dozen examples using an ellipsis to represent a blank space. Today's standard block size is 16 bytes. There is no high-frequency English phrase that long. There could be some long contextual phrases such as United States Government, Executive Committee, International Waters, and so forth. However, to produce repeated ciphertext blocks, these plaintext repeats must align the same way with the block boundaries. For example, 16-byte plaintext blocks, United ellipsis States ellipsis Go, and Knighted ellipsis States ellipsis Gov, would not produce recognizable ciphertext repeats when you are using a strong block cipher. The problem of repeated ciphertext blocks disappears when you use block chaining, section 11.9. With block chaining, any block size 8 bytes or longer can be used. Section 12.2. Long keys. We know that a secure cipher must have a large key to prevent a brute force attack. The current standard is a 128-bit key. If you need your messages to remain secret for 20 years or longer, I recommend a minimum of 160 bits. That is equivalent to about 48 decimal digits, 40 hexadecimal digits, or 34 single-case letters. If you are typing the key by hand, I suggest that you structure your keys in a uniform way. Divide the key into blocks of equal size with a consistent format. Here are 2 styles of uniformly structured keys. In the first style, all of the characters in each block are of the same type, uppercase letters, lowercase letters, or digits. In the second style, the blocks have the same format, 2 uppercase letters and 3 digits. The first of these 2 keys is equivalent to about 191 bits, and the second is equivalent to about 174 bits. For long keys like these, you must be able to see the characters while you are typing, so that you can review them and make corrections where needed. When the key is complete, the application should display a checksum so you can verify that the key is correct. One advantage of this regularity is that it prevents mistaking a letter O for a digit 0, or a letter I for a digit 1. I do not recommend random mixing of characters like $V94H semicolon T curly bracket equals capital N lowercase d circumflex 8 because it leads to mistakes. If you have a data file encrypted using the key $V94H semicolon T curly brackets equals uppercase N lowercase d circumflex 8 and you decrypted it using the key uppercase $V94H semicolon lowercase t curly brackets equals uppercase N lowercase d circumflex 8, that data file could now be unrecoverable. You may never figure out what went wrong and how to fix it. Using uniform blocks in your keys helps prevent such disasters. Another form of key that helps to prevent typing errors is artificial words. Make up your own pronounceable letter combinations, like this. Try to avoid patterns such as using the same vowel combinations, Palek, Mafna, Vardal, Glabit, and the like, where all of the words use the A-E vowel pattern. These alphanumeric keys can be converted into binary form by software. The MAD Ripple cipher, section 11.8, is well suited for this task. An alternative to typing the keyword for each message or data file that gets encrypted is to use a keyword manager that generates the keywords and associates them with the messages or files. The keyword manager could be installed on a website accessible to both Sandra and Riva. This topic will not be covered in this book. Note that a keyword manager is different from a password manager because Sandra and Riva, working on different computers, must use the same keyword for each file. Section 12.2.1 Redundant keys. In some cases, it may be possible for Emily to devise equations that relate the ciphertext to the plaintext and the key. If Emily knows or can guess some of the plaintext, these equations may make it possible for her to determine the key. For example, she may know that some of the messages begin with attention in all cap letters. This might be sufficient for her to solve a 64-bit key when an 8-byte block size is used. One way to defeat this potential attack is to enlarge the key. For example, if the block size is 64 bits, but the key is 32 bits larger, namely 96 bits, then you would expect, on average, that there would be about 2 to the power 32 possible keys that transform the known plaintext into the ciphertext. Emily would need to sift through these 2 to the power 32 solutions to find the correct one. This could be a difficult task because many of the more than 4 billion possibilities could look like plausible text. Enlarging the key will make Emily's task much harder, but not necessarily impossible. If she has twice as much known plaintext, then the equations for 2 cipher blocks might be used to solve for the key. However, it is much rarer to have that much known plaintext, and solving twice as many equations may take far longer than merely twice as long. Depending on the type of equations Emily is using, it may be feasible to solve a set of 64 equations, but not a set of 128 equations. If Emily does not have solvable equations, then redundant keys serve to make a brute force attack far more difficult and costly. Either way, redundant keys make Emily work harder.